Hello and welcome to the third in our series of demos of the functionality of securiCAD. In this demo we are going to show you some of the analytical capabilities of securiCAD. So to recap from previously, we have in front of us the view of the model which we developed in demo number 2. I'm just going to calculate this model to bring us back to the position that we were in at the end of that demo. You can see from the model that at the top of the screen we have an attacker that has access to the Google Chrome client running on a Linux workstation which has network connections through the internet, through a router with associated firewall, onto an Office network and to our host Windows server, which supports a service running an Oracle database and has connected to it a data store. The attacker has a connection through the browser to this Oracle database, and what we're most interested in is whether the attacker can reach the data store down here and access data of their choosing, and if so, what changes can we make to the model and its defenses to mitigate the most aggressive attack paths. First, I'd like to show you a bit more detail about this model. There is more to it than you can see in the simple view displayed. If I click on the database service and click on the black arrow to the left, you can see the objects that it is connected to. Some, such as the data flow, are already shown in the initial view, but some are not. And in particular, I want to show you this Oracle database software product. I click on that and just drag it into a convenient position. In securiCAD, a service always has a software product associated with it, where you can think of the service object as representing the executable code running on the host, in this case with non-root application execution privileges, and the software product represents the proverbial shrink-wrapped package from which it was installed. If I click on the product itself, you can see from the attack tab up here that there are a range of attacks that are applicable to a software product. Essentially, they entail finding vulnerabilities and exploiting them. If we focus on finding vulnerabilities, we can see that securiCAD uses different attack steps according to whether the vulnerabilities are patched or not. A software product also has a set of defenses associated with it. So these are the factors which affect how secure some code is likely to be. So for example, does it have vendor support? If not, then vulnerabilities that are disclosed will not have patches developed for them. Another factor is whether the software has known vulnerabilities which are patched or not. What sort of language was it written in? Was the code scrutinized? Is the binary code secret or publicly known? Is the source code secret? And what sort of code analysis was undertaken? We have a set of default values which you can see, but as with all defenses, we can switch them on or off or assign a probability to them. The defensive attributes determine which attack steps are applicable and how long it is likely to take an experienced attacker to complete them. So for example, the time to complete the attack step of find public patchable vulnerability will be influenced by the value of the attribute no patchable vulnerability. In this case, the attribute is set as off, meaning that there is at least one vulnerability that could be blocked by patching. In securiCAD, defenses are always described such that off is more vulnerable than on. If we go back to the Oracle database, we can see that there is a defense, an attack step described as find exploit. The probability of an attacker being able to find an exploit is influenced by whether there is a patchable vulnerability and whether the software is actually patched. Because the executable software is patched rather than the software product, we find a defense of patch under the service object. So here we can see that in this case, the Oracle database has a probability of being patched of 0.5. So I'll just tidy this back up a little bit, and I'm going to show you a bit more about how the attack path analysis and what we can learn from that. As before, we had a situation in which the probability of the data store being read after 50 days was 29%. Quite commonly, when we repeat a calculation, we will get a slightly different value. This, as it turns out, is just the same value that we had at the end of the previous demo, but because securiCAD uses a Monte Carlo approach to predicting probability of compromise, it will vary between 1 or 2% from value to value. If I want to look at the details of attack paths, I can do so by expanding the attack path through this pane here. I click on the data store read, and little boxes will start to expand the attack paths, which we can see here like so. If we look at the very last step, data store.read, you can see the attack step format comprises an object data store and an attack type, in this case read, and the number in 25 in brackets is a unique object identifier. You'll see that the next two lines, data store.encrypted and Windows server.compromise, are separated by this double ampersand, and also we see that the data store.encrypted is in grey and the Windows server.compromise is in black. The grey colouring signifies that this this is a defensive step which has not been set, and the ampersand means that for the data store to be read, that both of these statements here have to be true, i.e. the Windows server has been compromised and the data store is not encrypted. If I look below those steps, we see the next 6 steps all have the same level of indentation, and they're all in black, and there are no ampersands between them. So this means that the Windows server can be compromised by completing any one of these attack steps. If I click on these attack steps, you will see the change in the time to compromise graph at the bottom. It now shows time to reach the step that I have just clicked, in this case Windows Server bypass anti-malware, and you can see to reach this step there's a 22% probability after 50 days of attacker effort. If I click down the other steps, you can see it varying, very low for this particular route. RDP.compromise is our most vulnerable attack path because we can see the probability is 29%, which is what we had for all attack paths. RDP is a remote desktop protocol. It's commonly implemented in Windows Server operating systems, and this is an example of the common rule that if you don't need a particular protocol, your system will be more secure if you switch it off. I could switch it off in this model. If I do so, it only makes actually a small difference to the time to compromise because of these other attack paths. If you're wondering where the RDP features in the model, then it's, if I click on the host Windows server and the black arrow, you can see it appear as one of the components within there. I'd also like to show you another tool for analysing attack paths. If I come back to the read step, you'll see this tab at the top right, and visualize critical path is now enabled. If I click on that, we see a new representation of attack paths. As the representation first emerges, you can see it's somewhat tangled. I can untangle it by dragging these icons around, but I'm going to cheat a little bit and use one that I prepared earlier, which is this one here. It's exactly the same model as you saw before, but now I've put the whole attack path on the screen and goes in this zigzag fashion to fit it on to the screen. You'll see it starts the attacker's entry point up here, compromises the Google Chrome browser as we saw before, and this, the most vulnerable attack path, passes through the data flow request, Oracle Database Connect, up to database find exploit, across to deploy exploit. Then as I go on through, you'll see it pass through to the Windows Server user access, find a public patchable vulnerability, find an exploit, deploy the exploit, bypass defenses on the server, and you reach the Windows Server compromise, which enables a data store read. One thing I'd like to point out on this, as you progress down an attack path, as I click on each of these icons, you can see the time to compromise to reach that particular step. And generally, as we progress down the path, the time to compromise naturally increases. We're still at 1 day here. As I reach find exploit, you can see we're now up to 5 days. If you're wondering where these times come from, then there's quite a lot of details on the foreseeti website on our research and development pages. But essentially, they come from structured consultations with experienced penetration testers, and also an analysis of the times between vulnerability disclosures by experienced vulnerability analysts. So, as I said, the time to compromise appears as I click on each of these icons. I've reached 5 days at this point. As I come down to here, I come to deploy exploit, we move up to 38 days, still 38 days, now at 52 days. But when I come to Windows Server, you'll see it drops back down to 38 days. Now, the reason for it dropping back down is because there are many other attack paths which are not shown on this visualization for the sake of simplicity, and it means that some of those attack paths converge on this Windows Server and do not go through the Oracle database. When securiCAD calculates time to compromise, it makes a simplifying assumption that an attacker can explore all attack paths concurrently. So when it takes into account all possible attack paths, the time to compromise will be shorter than the time to compromise from any single attack path, and often it will be shorter than any single attack path, even if that is the fastest attack path. So that's the reason why sometimes the time to compromise drops as you go down a single attack path. I'd like to show you a bit more about from this diagram. As I click on the level of detail here up on the left, it will show more of the possible attack paths. As I reach this point here, if I now expand out a bit, you can see that it shows a completely new attack path, and this is basically the route through the infrastructure. So as you can see, we start up again from the Google Chrome client, then it goes to the Linux workstation rather than following the data flow, and you can see it go down through that workstation, bypassing defenses, compromising it, then crosses the internet, finds a hole in the firewall through the router, office network, and you'll see it come to the Windows Server and deploying an exploit, bypassing defenses, and to the Windows Server compromise, which again leads to it being able to read the data store. One thing I want to show you now is how we can infer from these types of visualizations which actions we might take to reduce and mitigate attack steps. If I go back to our critical path here, there was a key step of finding an exploit on the Oracle database. These green shields indicate defenses which could have been set but which have not been fully set and which would affect attack paths. So in this case, this green shield is indicating that the Oracle database is not fully patched. So we can go back to the model and actually patch the Oracle database. So I click on that and then I click on defenses, and we see here the defense for the service of patching. It has its default value of 0.5. I'm going to change that to on, so it's fully patched. For now, we can show you what's happened to our reference point, the probability of a read after 50%, after 50 days of effort. You see our old reference point was 29%. If I recalculate to take into account the new level of patching, we'll see that change in our case to 19%. So there's another thing which I'd like us to consider on this particular attack path. Even when the service is fully patched, securiCAD takes into account the probability of an attacker finding a 0-day exploit, i.e. a vulnerability that has not been publicly disclosed previously and for which there is no patch. So we might think that for the attackers we have in mind, that's unrealistic. So if we thought that, we might want to be able to switch off that particular type of attack step. And we can do that by modifying the compromise attack step as follows. I just bring this down a bit. I now click on the Advanced tab here. We see a range of probability distribution functions, different types of statistical distributions. And if I come to the bottom option, infinity, it will effectively say that it will take an infinite amount of time for the attacker to complete the attack step, so it's effectively disabled. So if I click on that and fold that back up again, and let's see what's happened to our favorite reference point. So we were at a 19% probability of compromise after 50 days. I come back to recalculate, and you'll see it's now dropped to 11%. Now I'll show you the impact that has had on the critical path. If I just run that again, I get a tangled initial response, and I'm going to cheat again by showing you one that I arranged earlier. So this is it, attacker's entry point. Starts with a Google Chrome client, but instead of heading towards the Oracle database, you can see it now heads towards the Linux workstation, and it finds its way through an exploit on the Linux workstation and through the other infrastructure route that we saw before. Another point I like to explain that you can learn from these diagrams is the significance of the thickness of these arrows. You'll see that some arrows are thicker than others, and the thicker the arrow, it means the more commonly used that particular attack step is. So what this is telling us now is that most of these, if not all of these attack steps, go through the firewall. And this green shield is telling us that there's a defense which has not been fully set, and it's this defense of known rule set. What the known rule set means is that the rules in the firewall are consistent with the data flows in the model. So if the rule set is fully known, all the data flows in the model will be reflected in the rules in the firewall and no more than that. So we might believe that our firewall is correctly configured to only permit through the data flows that we expect. So we might want to adjust that defensive setting. So I come back to the model. The firewall is actually within this container here. If I click on the black arrow, you can see it emerge as the firewall there. If I click on the firewall and go to defenses, we see known rule set. It has a default probability of 0.5. I'm going to change that to on. So I'm now going to show you what difference that has made to the time to compromise. Let's come back to data store and the attack of read, and we had that probability of 11% compromise after 50 days. Let's just recalculate that. Just wait for that to go through, and you see the probability has now dropped down to 0%. And if I click on the visualize critical path, it tells me no attack path was found for this attack step, i.e. reading the data store. So what this is saying is that we've now blocked off both the attack path through the application layer and the attack path through the infrastructure. So that just illustrates a few of the analytical capabilities of securiCAD. I have shown you how we can use the model to explore attack paths and the defenses against them, and how we can use it to model the consequences of design changes. However, we have to remember that it is just a model. When it says here that there is no attack path, it doesn't mean that your real systems are 100% secure. Unfortunately, it just means that our models are not 100% accurate. It's just a representation of the complexity of a real system, but it still captures a lot of useful system security information. And if we want a more detailed analysis, the model is a useful reference point in the analysis process. So that's all, and thank you for listening.